Hello everyone. Today we are going to study one more practical in the subject of heat transfer. The aim of the practical is to determine heat transfer coefficient in forced convection mode. This is our experimental setup for this purpose. First of all, we will understand what is the physical significance of heat transfer, how it is applicable or how it is important for engineers. Then we will understand the experimental setup. Then we will understand the calculations and readings which are to be taken, the calculations which are to be performed during this experimentation. So first of all, why forced convection is important or how it is created. Whenever during the process of heat transfer, whenever we are creating a fluid motion because of external force, then it will be termed as forced convection. The simplest example is that of drinking the tea. For example, if I am having tea in a saucer, and if I am drinking it just like it is, whatever the temperature it is having, then the tea will get cooled off only because of natural convection. But if I am blowing air on it artificially or with the help of external force, then it will be termed as forced convection. If you go to the industry, in a boiler, when you are circulating water through the tubes, then it is done with the help of external mechanical force which is given through the pumps. And that's why that kind of convection will be forced convection. If you go to the refrigeration industry, let us say you are cooling a refrigerant in a condenser. You are circulating it through all the condenser tubes with the help of pumping or through the compression. Then it will be termed as forced convection. So there are tremendous applications of this. The main purpose of the forced convection mode is to increase the heat transfer rate, because heat transfer coefficient is more in forced convection than heat transfer coefficient in natural convection. Now we will get to the setup. So we have created forced convection with the help of this air blower. Remember, this is air blower. This is not an air compressor. Its function is not to create a very highly pressurized air. Its function is to create only air having larger volume flow rate. Its function is to provide higher flow rate. For example, if atmospheric pressure is 1.01325 bar or 101.325 kilopascal, then this may generate pressure of air hardly up to 1.1 or 1.2 bar. But volumetric flow rate through the system will be much larger. So, once we start the blower, it will start circulating air through this pipe. We will be taking the reading of internal diameter of the pipe. So, from this end, the air will enter into this test section. Why we are calling this as test section? It is supplied with electrical heater arrangement. So this particular part of the test section, it will be heated because of this electrical heaters. Cold air will enter into the test section at this point, and then it will come in contact with the heated surface. It will absorb the heat from the surface and it will exit on the other end. Afterwards, air will keep passing through the pipe. Then it will face this orifice meter. This particular orifice meter is plugged in with these two pressure manometer limbs so that we can measure the pressure. We know the working principle of orifice meter from our second year fluid mechanics. At the inlet, the pressure will be higher. Then at the orifice meter, there will be sudden reduction in the area. Because of that, there will be reduction in the pressure. Because at the inlet pressure will be higher, so there will be a kind of depression in the left limb of the manometer. The level of the water will be less. On the right hand side, once air has passed through the orifice meter, the pressure will drop, and that's why pressure in this second limb, that is limb on the right, it will be less, and that's why level of water will be high. Remember, pressure is inversely proportional to the level of manometric fluid. Left limb, pressure more, that's why level of the water will be less. In the right limb, pressure will be less, and that's why level of the water will be higher. Because of this, we will get the pressure difference between the two limbs, and that will be required to calculate the flow rate. There are 6 thermocouples which are mounted in this test section. First thermocouple and 6th thermocouple, they will tell us about the inlet temperature of air and exit temperature of air. Exit temperature of air will be more than the inlet temperature. Thermocouple 2nd, 3rd, 4th, 5th, that is T2, T3, T4 and T5. they will tell us about the temperature of surface. This is a convection heat transfer, and according to Newton's law of cooling, the convection heat transfer is given as heat transfer coefficient H multiplied by surface area AS multiplied by temperature difference, that is Ts minus T infinity. So we will be able to get these quantities. Now this practical is slightly different than the practical of natural convection. In this case, only a particular section of the pipe is heated. Also, not entire heat is getting transferred to the air which is flowing on the inside of the pipe. Some air is getting lost to the insulation, some heat is getting lost to the insulation, some heat is getting lost to the atmosphere. And that's why, first of all, we will calculate mass of the air, then we will calculate the quantify the heat transfer to the air with the help of expression mCp delta T. That delta T in that case will be temperature difference of air from the inlet to outlet. And once it is done, we will be able to compare the amount of heat which is supplied and amount of heat which is received by the air, and at that point we will be able to calculate heat transfer coefficient H. In second year, we have understood something called as Bernoulli's equation, and orifice meter is the application of that Bernoulli's equation, which means that at the inlet, which means in the left limb, at the inlet pressure will be more. So that's why there will be a depression created in the manometer limb. Once air passes through the orifice meter, there is sudden reduction of the area. Due to sudden reduction, there will be increase in velocity, and that's why reduction in pressure. That reduction in pressure will be measured by the second limb, which means the limb on the right. And that's why there will be rise in the level in this particular limb. The manometric fluid which is used in here, it is water. It is not mercury. Why we are not using mercury in here but we are using water? In fluid mechanics, in all the practicals of fluid mechanics, we have used water as the working substance and we have used mercury as the manometric fluid. But in this case, the working fluid is air only, which is having very low density. And water is having a density of 1000 kg per meter cube. Density of air is hardly 1.19 kg per meter cube. So if we use mercury in the case of this manometer for forced convection apparatus, then actually it will not create any kind of movement in the limb. We will not be able to read the pressure difference. And that's why we do not use mercury in this. We use water as the manometric fluid in this particular practical. So now we have understood the setup components. We will switch on the setup. Before that, you should notice one thing, that in this manometer, both left limb and right limb, they will be showing same water level because the pressure is now atmospheric pressure in the left limb as well as in the right limb. Once setup will be started, once blower will be started, there will be lesser water level in the left limb and there will be more water level in the right limb. That we will observe once the blower has been started. So we will switch on the blower now. Once you switch on the mains switch, there will be temperature indicator which will be switched on, the voltmeter and the ammeter. The amount of heat supplied will be the product of voltage and the current. Why? Because this is a single phase setup. Electricity is supplied in the single phase, so product of voltage and current will give you the amount of heat which is supplied to the experimental setup. Also, we can change the temperatures. In the sense, we can see T1, T2, T3, T4. Now you will see that all the temperatures, T5, T6, all the temperatures are indicating the same value because right now they are at the atmospheric temperature. So right now I am back to T1. So now I will switch on the blower. The heater, the dimmer stat, actually this will help us to create resistance in the path of electrical network. And see, once we are rotating it, the voltage is changing. So let us say we set voltage to some 50 volt or 55, 60, whatever that you want as per the specification in your laboratory. Now we will switch on the blower. Remember, we will record the readings only when steady state is achieved, which means the temperatures can change with location. but they will not change with time. Only then and then we can say it is a steady state behavior. Now I will switch on the blower. So it will be a noisy experiment, but remember, as compared to the other experimental setup, this setup requires lesser time to achieve the steady state. For example, other setups may require 1.5 hours or 2 hours, but this setup will require only 30 minutes or 45 minutes to reach to the steady state. So once Okay, now the setup has been started. It is going to achieve its steady state after some time. In the meantime, I will show you the change in temperature. Right now, I'm trying to keep my voice as close to the camera as possible. Right now, it is showing me the value of T1 and the T1 is 28 degree. If I check, the T2 has increased 35. T2 will be somewhere here on the test surface. Then the temperature T3, it is more, T4, T5, and finally you will see the temperature T6. You will see that surface temperature is higher and air temperature is lower. One more thing you should note is the change in the level of manometric limbs. In the left limb, you will see that this is the level of water. In the right limb, this is approximately the level of water. If your manometer is somewhat what we can say not clean or not visible properly, we can change with the help of this particular action. We can restrict the airflow like this, and immediately when I do this, the readings in the manometer, they will fluctuate. In this way you can find out the levels, that where exactly is the level and the difference in those two levels, which means right now this is at 90 mm on the right hand side and it is on approximately 50 mm on the left hand side. So 40 mm is the difference in pressure in terms of water column, which afterwards we can convert so that we can get the volumetric flow rate of air. Voltage is 60, current is 0.447 approximately. So ultimately that product will give us the rate of heat transfer to the experimental setup. Next part will continue in the calculation mode.
So welcome back everyone. Now we are moving to the second part of our practical, that is calculation of the readings which are obtained from the experimental setup. These readings are recorded only after steady state has been achieved for all the parameters. So which are these parameters? You will be recording voltage, current, the difference between the two limbs of manometer, that is H1 and H2. Thereafter, you will be recording temperatures T1, T2, T3, T4, T5 and T6. Remember, the temperature T1 and T6, these are entry and exit temperatures of air, while T2, T3, T4, T5, these are surface temperatures. So, now how should we proceed with the calculation? Remember that our ultimate objective is to find out how much is heat transfer coefficient. For this purpose, because it involves number of calculations, so we will simplify our understanding of what exactly we need to do if we want to obtain the heat transfer coefficient. So the basic logic that I want to tell is this one. You should only understand the energy balance. The energy balance tells us that whatever is the heat which is received by air, it is received because of convection. So how to quantify this now? The concept is there, but then how to quantify this concept? So Q air. One thing I will scribble down on the right hand side. There are some things physically that we need to understand about Q air. The first thing is that air is already present in a gaseous form. Second thing, when heat transfer is happening, there is only change in temperature of air, which means this is sensible heat transfer. And it is not a latent heat transfer. Remember, latent heat transfer is not happening. So it means that we can quantify because there is no phase change, that's why there is no latent heat transfer. So we can quantify the amount of heat which is received by the air with the help of our basic formula, that is mcp delta t. So as soon as delta t comes into picture, we should immediately understand that mcp delta t will be applicable. We will apply this mcp delta t parameter to the air itself. So we get the left hand side of the equation, that amount of heat received by the air will be equal to mass of air multiplied by cp of air multiplied by delta t of air. One second. Okay, so this understanding is, I think, clear now. Once this is done, we need to go on to the second part of the equation, that is q convection. So this is as per your Newton's second law. My mistake. As per Newton's law of cooling. So what does that tell you? It tells you that amount of heat transfer by convection is equal to HAS into TS minus T infinity. This is the mathematical expression of Newton's law of cooling. In this case, H is the heat transfer coefficient, AS is the surface area of that channel or of that surface, TS is the surface temperature, T infinity is the fluid temperature. So we will put this equation here. So HAS into TS minus T infinity. Remember, you should notice one thing. Delta T which is on the left hand side is different. Delta T which is on the right hand side is different. If I write this delta T, notice that this will be C mass of air as it is, Cp of air, and delta T for air only. So delta T of air means exit temperature of air minus entry temperature of air, whatever is the temperature difference created for air only. So this will be T6 minus T1. It is equal to H multiplied by AS is nothing but the surface area of the pipe through which air is flowing. Remember, there are two types of areas for a pipe. One is surface area, one is cross-sectional area, because this air is contacting the entire surface of the pipe. For example, if I draw the pipe here itself, let us say this is one end of the pipe and this is the second end of the pipe. So in this case, air is entering into the pipe. The pipe is at some higher temperature. Let us say the pipe was at some higher temperature of 35 degrees Celsius, while in our case air entered at about 28 degrees Celsius. Then pipe has given heat to the air has been heated, and then air is coming out. So air is coming out. So in this case, air is contacting this entire surface of the pipe. That's why we need to take the surface area. So many times student confused with the cross-sectional area. So remember, this much section, only this much, pi by 4 d square, this much is the cross-sectional area, and air is not contacting only cross-sectional area, but air is contacting this entire length of the pipe. So the pipe has some diameter, air is contacting some length. So it means that the total surface area of contact of air with the pipe, it will be pi dl, and it will not be pi by 4 d square. No, this will not be applicable. So I hope again this understanding is clear. So I will just erase it. Then, so AS is pi into internal diameter of the pipe, because air is not flowing over the external diameter, it is flowing only through the internal diameter, multiplied by L, multiplied by Ts minus T infinity. Now, this simple understanding is there if you observe that if somehow we get all the parameters, for example, if we can calculate mass of air, we can obtain Cp of air, T6, T1, these are from the experimental setup, diameter and length of the pipe is given, Ts, it is again obtained from these four values, average of T2, T3, T4 and T5, T infinity, that is fluid temperature, it is average of T6 and T1. So if we are able to obtain all these parameters, pi is already a constant. So the only unknown parameter in this case will be heat transfer coefficient. So immediately we will be able to obtain that. That is the basic logic with which we will be operating. So now, how to proceed with this? First of all, I will like to proceed with the Ts and T infinity because these are somewhat simpler parameters. So Ts is nothing but the surface temperature of test section. So that is surface temperature of test section. And this Ts is nothing but T2, T3, T4 and T5, their average, divided by 4 degrees Celsius. So instead of showing you only formula, I will also put down the values. In one of the practicals that we performed, we had some readings. So I will put down these readings here. The voltage that we found, it was 80 volt. These are the readings after steady state. Remember, the steady state may take 15 minutes or 30 minutes or 45 minutes depending on the size of the setup. The current that we faced, it was about 0.579. And then H1 minus H2 was 33 mm. Then T1 32, T2 52, 57, 58, and then 57, and finally 39. You can see that the air temperature has increased from inlet to outlet. At the inlet the temperature was 32, at the outlet air temperature is 39, which means air has gained the heat, and that's how we can write mcp delta T for air. Okay, so now because we have the values of temperature, we can obtain Ts as average of 52, 57, 58 and 57. So this is 52, 57, 58 and 57 divided by 4. So it implies that your Ts is equal to, I will just do it in front of you in the calculator. So 52, 57, 58 and 57 divided by 4. So that is equal to 56 degrees Celsius is the Ts. And as I always tell my students to bracket the answer because this value will be required somewhere else. And then we will be going for T infinity, which is temperature of air. So that is equal to T1 plus T6 divided by 2. And here we have 32 and 39. It implies that T infinity will be equal to so 32 plus 39 divided by 2. So 35.5 is T infinity. Okay, so now we have Ts. See, one by one we will be obtaining the parameters. Internal diameter of the pipe, in our case in experimental setup that we have in our laboratory, internal pipe diameter is 28 mm and length of the test section is 400 mm. So we will be using that. So di is 28 mm. I will be immediately converting it to meter. So 28 divided by 1000, let us confirm it, it will be 0.028. So 28 divided by 1000, so 0.028 meter, it will be the value of di. In the same fashion, the length of the pipe or the test section, actually only the test part of the section, that is 400 mm. So that is equal to 400 divided by 1000. Immediately I will be converting it to meter. It is apparent that it will be 0.4 meter. Still 400 divided by 1000. So that is, it implies that your L will be equal to 0.4 meter. Okay, so we have now di as well as L. H is still unknown, T6 we have and T1 we have. Cp of air, we know that Cp of air we can obtain from the data table, or we can simply take it as 1.005 kilojoule per kg Kelvin, or we can also go for the interpolation. Presently the temperature range is not much, that's why we can take Cp of air as 1.005 kilojoule per kg Kelvin. But remember, heat transfer will be in watt. Also, unit of heat transfer coefficient, remember, unit of heat transfer coefficient will be watt per meter square Kelvin, and that's why we need to convert this kilojoule into joule. So it implies that your Cp of air, this is equal to 1005 joule per kg Kelvin. Okay, so again one more input we have from our basic equation. Yes, now the question will come that only one parameter is remaining to be calculated. It is mass of air. Now how do we calculate this mass of air? And this is the part where efforts are required from the students. So we will use our basic fluid mechanics. Mass of air will be simply equal to density of air multiplied by volumetric flow rate of air. This comes from the definition of density itself. We know that density is nothing but mass per unit volume. So if we want mass, then we will keep mass on one side and multiply density with volume. That's it. Now in this case, one thing yet to be remembered, here not only mass of air is there, but actually it is mass flow rate of air, and because of that we will express the mass flow rate with the help of m dot symbol. And density cannot be rate, but volumetric flow rate is there, so it will be volumetric flow rate. So that's why m dot of air is equal to rho of air multiplied by v dot of air. So it means we need to calculate rho of air and v dot of air so that we can calculate mass flow rate of air. So firstly we will proceed with density of air. So for this purpose we will use ideal gas equation. So what does the ideal gas equation tell us? We know that PV is equal to mRT with the help of ideal gas equation. So in this case we are interested in the density. So mass per unit volume is density. So mass divided by volume on one side and everything else on the other side. So pressure divided by R into T on the other side. So it means that if we want density for an ideal gas, it is equal to pressure of the gas divided by R of gas multiplied by temperature of gas. Which means if we want density of air, then it will be equal to pressure of air divided by R value for air. R is specific gas constant, T is temperature of air, the product of R and T. This will be our formula for density of air. Now, during the explanation of experimental setup itself, I have explained that experimental setup or blower is not going to change the pressure of air very much. It is only going to create a significant volumetric flow rate of air, and that is why P of air can be taken as 101.325 kilopascal. So this P of air is sorted. Fine. R of air is known to us as 0.287. So I will just put down these quantities. So the first thing is P of air. It will be as good as atmospheric pressure. So atmospheric pressure is 101.325 kilopascal. Then the next thing is R of air, that is equal to 0.287 kilojoule per kg Kelvin. Remember, if you are taking pressure in kilopascal, you have to use R in kilojoule per kg Kelvin. So many times students make a mistake. They tend to write it as 287, or even sometimes they write it as 8.314, which is universal gas constant. It is not applicable here. So R of air is there, P of air is there. What about T of air? T of air, actually T infinity, we have already obtained that here. So we just need to convert it into Kelvin. Always remember, in case of ideal gas equation, temperature is always in Kelvin. So it means that temperature of air, it is equal to 35.5 degrees Celsius. So that is equal to 35.5 plus 273. Now we can calculate this in calculator. So 35.5 plus 273, that gives you 308.5 Kelvin as the temperature of air. All right. Okay, so the page has been finished. Fine. So now we have T of air as well in this case. So it means now we can calculate the density of air. So it means that if we want density of air, that is equal to 101.325, that is P of air. R of air is 0.287 multiplied by temperature of air, that is 308.5. So it means that density of air, I will do it in the calculator in front of you. So 101.325 divided by, sorry, actually I am habitual to old calculator. So 0.287 multiplied by 308.5. So 1.14 kg per meter cube is the density of air. Remember, if you are putting pressure in kilopascal, then value of R must be in kilojoule per kg Kelvin and temperature must be in Kelvin itself. Also, I can do the same thing with the help of the general calculator also, that 100 ms or 991 ms. You just need to do this thing, 101.325 multiplied by, divided by, for the entire denominator you need to open the bracket, put in the product, that is 0.287 multiplied by 308.5. See, if you manage the brackets properly, you get the same answer. So no need to worry even if you do not have this ES type of calculator. Fine. So density of air is obtained. So don't forget about this equation. This is what we are dealing with. So density of air is obtained. Now we will focus our attention on volumetric flow rate of air or discharge of air, that is V dot. So in the experimental setup, we are using orifice meter to obtain the volume flow rate of air, and that is why the formula for the flow rate of air, it will come from the basic of our fluid mechanics. So that will be equal to coefficient of discharge multiplied by pi by 4 into d0 square, that is diameter of orifice square, multiplied by the velocity component, which is indicated like this, root 2 g hw into rho w upon rho a. Now so many times this question is asked in the oral examinations, that how this particular bracket is created. So remember, dear students, this equation is not a very different equation. It is simply a modified form of your continuity equation. If you look at continuity equation, it tells you that volumetric flow rate is nothing but area multiplied by velocity. That's it. So if you observe here, this is the cross-sectional area component. Already d0 is the orifice diameter. So already area component is there in this equation. What about velocity? In general, you write the velocity of the fluid which is passing through that orifice or which is passing through the pipe as root 2 gh. 2 is constant, g is acceleration due to gravity, h is the pressure head which is creating that velocity, again from the basics of fluid mechanics. So how do we treat this h? In this case, this fluid is air, so this should be h of air, but instead you will observe that there is no h of air in this particular equation. This is because we are not using a manometer which is having air inside it. We are using a manometer which is using water to indicate the pressure of air. So by logic, whatever is the pressure of air, it is being indicated as the pressure of water, and this is again from the basics. So the very basic rule of pressure or very basic equation of pressure is that pressure is equal to rho gh of that particular fluid. So if the fluid is air, then same formula will also be applicable rho g h of water, because pressure is equal. Whatever is the pressure drop of air, it will be indicated by water. There is no different pressure in the system. So let us split the terms for the simplification. So it gives us rho of air multiplied by C. G will be same for air and water, they will not be different, into H of air, head of air. So it is equal to density of water multiplied by GH constant multiplied by head of water. So G will be cancelled on both sides. We are interested in head of air. How much head of air will be created, or how much pressure will be created in terms of air column? That is very difficult to measure because density of air is very less. So we will require a very large column even if we want to measure a very small pressure. So that's why we use water as the manometric fluid. So if we simply rearrange the terms, what do we get here? That rho W as it is multiplied by HW as it is divided by rho of air. So if you observe, this is the same formula which is present in this bracket. HW rho W upon rho of air. So we are actually talking about this velocity component through this bracket, and again for this H of air we have this particular equation. So ultimately, I hope this understanding is clear. We are not doing anything differently. There is no rocket science. We are just using our fundamentals of fluid mechanics so that we can arrive at the discharge rate of air through the orifice meter. So I will just erase this, everything now. I hope this understanding is clear. Thereafter, now how to do these things? CD, that is coefficient of discharge of the orifice meter, it is known to us, it is 0.64. So I will put it here, that is 0.64. Then pi by 4 as it is. In our experimental setup, the diameter of orifice, just give me a second, I'll check it. It is given as 14 mm. So that is equal to 14 divided by 1000. I will immediately convert it into meter, so you can do it in a second. Actually now you should do it by memory itself. So 14 divided by 1000, that is 0.014 meter. I will suggest you do these things parallelly while watching the video. Only watching the video will not be helpful. So you learn more by doing it rather than only watching the video. So 0.014 multiplied by, in the bracket, so I will delete this just to create the space. So D0 is sorted, actually my mistake, not only D0 but the square of this. Okay, then 2 into value of G is 9.81, HW, which is the height of water column. If you recollect, this is the parameter that we have obtained here. So height of water column is 33 mm. So that is actually 33 divided by 1000. I will not calculate this time. So that is equal to 0.033 meter. You can check it once again on the calculator. So it is 0.033 meter multiplied by density of water. We already know that, that is 1000. Okay, divided by rho of air, you just calculated this parameter, so that is 1.14. you see that there is no rocket science in this, it's just plain simple basic application. So we will calculate this in Calc now. 0.64 into there is this pi, yes, shift pi by 4 into 0.014, that is pi by 4 d squared, one second, multiplied by square root of, now this square root is again in the terms of numerator and denominator, 2 G HW 0.033 into rho W divided by 1.14. So the flow rate comes out to be 0.00234. That is your answer. So I will just put it here. So flow rate is 0.00234 0.00234. Unit of this will be meter cube per second. Sorry. Or sometimes it is possible your calci might provide you the answer like this: 2.34 into 10 raised to minus 3. Remember, it is one and the same quantity. Unit will be same, meter cube per second. So now you have V dot of air, you have rho of air. So ultimately now you can calculate mass of air. So now mass of air is equal to V dot of air, that is 0.00234 multiplied by density 1.14. So it means that mass of air, this, okay, 0.00234 multiplied by 1.14. So the mass flow rate of air, it is 0.00266 kg per second. Alright, so now we have mass of air. We will go back to the basics. In this basic equation, we needed this particular parameter, that is mass of air. So we have that as well. So mass of air, Cp of air, everything else is there. So only H is the unknown quantity that we will be now able to find out. So I will rearrange the entire thing. So mass of air, mCp delta T of air. So mass of air 0.00266, Cp of air 1005 joule per kg Kelvin, delta T for air, that is T6 minus T1. So T6 is, just give me a second, 39 and 32 is T1. So T6 minus T1, so 39 minus 32, this is equal to H into pi. The internal diameter of the pipe is 28 mm, so that is 0.028 meter. Length of the pipe is 0.4 meter into, so Ts minus T infinity, surface temperature Ts, I think we just calculated that. This is where the bracketing helps, 56 and 35.5. So Ts minus T infinity. You can take 1 minute to solve this. So the only unknown parameter here is H only. So we will put it. So simply 0.00266 into 1005 multiplied by 39 minus 32 divided by pi. D is 0.028, length is 0.4 multiplied by 56 minus 35.5, so 25.94. So the value of heat transfer coefficient which is obtained by experimental method, it is 25.94. Its unit will be watt per meter square Kelvin. This is how you calculate heat transfer coefficient in the experiment of forced convection with the help of readings and observations. This method is called as experimental method of obtaining the parameter. Experimental method. There is also another analytical method. उसकी बात किसी और वीडियो में करेंगे. Presently this much will be helpful to you. I hope you have understood it. Remember, we just put our entire equation, our entire exercise only on the basis of one equation, and only on the basis of this understanding that heat received by the air is because of convection heat transfer, and we applied all the basics and we went down to the individual parameter calculation, nothing more than that. So the value of heat transfer coefficient in forced convection is 25.94. When we performed the practical on natural convection setup, the value was approximately 10. So it indicates that forced convection heat transfer gives you higher heat transfer, and that is why it increases the rate of heat transfer. So I hope this was useful to you. We'll meet in the next video. Thank you.